Swayam Prabha. Digital India. Educated India.
Good morning everyone, and in today's module we are going to talk about the orbits of planetary motion. This is the first part of the lecture series and we'll primarily cover the three fundamental laws, the description as well as the derivation of the Kepler's laws of planetary motion. So let's start without delay. So the topic of our today's discussion is orbits of planetary motion or orbits in central fields. We'll talk about this concept of central fields in a little bit of time later. So this is the first part of our lecture series. The key concepts we'll cover in today's discussion are the ideas of radial motion, the path equation, the Kepler's laws, radial motion, the path equation, the Kepler's laws, the E formula, and finally the L formula. Okay, so it turns out that the next biggest thing after the three laws of motion by Newton were the three laws of planetary motion by Johannes Kepler, which came a few decades later. So these three laws were some of the fundamental rules governing the motion of planets in the presence of the central field of gravitation. So we'll right away just mention the three laws of planetary motion, and one by one I'm going to show you how do these three laws materialize through rigorous mathematics. So the three laws of planetary motion. This was by Kepler. And the three laws of Kepler were, so the first law was that each planet moves in a bounded elliptical orbit, right, with the sun at one of the focus of the ellipse. So the first law was each planet moves on an bounded elliptical orbit with sun at one focus of the ellipse. Okay. So we'll step by step we'll show all these laws, we'll derive all these laws, how we are getting it through rigorous mathematics. Sun at one focus of the ellipse. The second law mentions that the area swept by each of the planet at equal times is equal. So that's in short. So the full statement says for each planet the straight line connecting the planet to the sun sweeps out equal areas in equal time. Okay. The straight line connecting the planet to the sun sweeps out equal areas in equal times. And the third law, which is the most interesting one, is it provides a relation between the period of the planetary motion and the semi-major axis of the ellipse on which the planet is rotating. Namely, the third law says the square of the period, of course, of the planet was proportional to the cube of the major axis of the orbit. The square of the period of the planet is proportional to the cube of the major axis of the orbit. Okay, so the assumption here is that in the derivation of these three laws, the major assumption is that the planets are moving in a central force field with sun at one of the focus, right? And so it turns out that the mass of the sun is so big. Typically, it has been found that the mass of the sun is roughly 50 times more than the mass of all the planets, all the 9 planets combined in our solar system, right? So the mass of the sun is so big that essentially the gravitational force field is acting as if this is a one body problem. That is, only one body is moving. The sun is practically fixed in this entire interaction. Okay, so just now what I said was the assumption, there is a bit correction. The mass of the sun is not 50 times but 5,000 times the mass of the entire masses of all the planets combined. Okay, so assumption is that the single particle moving in a central force field with fixed center. So this is a one body problem. This is a one body problem, and the combined why do I say this is a one body problem? Because as I just said, the combined masses of all the planets and moons and asteroids is less than 0.2% of the mass of sun, right? So the masses, this is because the masses of all planets, moons, asteroids, etc., whatever is there in the solar system, is less than 0.2% the mass of the sun. Okay. So so essentially the motion of the sun is comparatively small. So sun is fixed. So this is what I mean by saying that this is a one body problem. The gravitation is minuscule for the sun. Okay, so then let us now, before moving ahead, let us first define what is a central field. Central field. So the central field is a force field which is acting along the radial direction, or it is acting along the direction combining. It is acting along the direction which is parallel to the line joining the two bodies under consideration. So a force field Fr is a central field with center O, central field with center O, if it has the form Fr, which is f of r hat, where R is given by, the R is a scalar, it's the distance between the two planets, and my direction R hat is R vector divided by the magnitude R, which is this quantity. Okay, so that's my radial direction R hat. So essentially what I'm saying is a central field is spherically symmetric about its center. A central field is spherically symmetric about its center. Okay, so what we have is, of course, one example that is what we are going to deal all the time is the case of a central field, which is the gravitational field. So an example which is present all the time is that of the gravitational field. Okay, so we have in this case the force field has the following form. This is minus m capital M, where m and capital M are the masses of the two bodies under consideration, times the universal constant g divided by r square r hat. Okay, so this is a radially symmetric field. Okay, so then let us quickly try to summarize. First, we will try to summarize the motion of the bodies in a central field, right? So equation of motion in central field. So let me denote central field by CF in future. Okay, so the fact is that so let me draw some diagram, because in all these problem involving physics, it's very helpful to have some reference diagrams. So what we have is, we have a particle P, and let's say we have the origin, some sort of an origin. Let us keep the heavier object, which is the sun in our case, to be at the origin O, and the planet is the particle which is moving, which is denoted by P, and let us say that that the perpendicular distance from the straight line of the planet to this sun is, or this origin is given by the distance P, and the radial distance of course is R, and let me call the radially outward direction to be VR, or the R hat, and we have that the tangential direction is theta hat. Okay, and let us say this planet is moving with a velocity v. So its velocity along the radial component of the velocity is Vr, and its direction along the theta direction is v theta, right? Okay, so what we have is, in a central, what we are trying to say, so this is a fact. The fact is that in a central field, CF, in a central field, each orbit of P lies in a plane through O containing the initial velocity and the initial position. Okay, so each orbit of P lies in a plane passing through the origin, which contains the initial velocity and the initial position. So we are talking about this 2D plane under consideration. Okay, so then we can quickly write down the Newton's laws of motion in this case in polar coordinates, because we are talking about radial and tangential directions here. The Newton's laws of motion in polar form polar form is as follows. We have the radial component is m times r double dot minus r theta dot square is fr, and we have m times r double dot minus plus 2 r dot theta dot is 0, right? And then these are the two components of the equation of motion. And we see that, let us look at the second equation in particular. We can see that the second equation is as follows. If we combine the two terms on the left hand side of the second equation, we get m times ddt of r square theta dot, right? And then there is an r outside. So if we differentiate this this quantity, we are going to get the two terms that we have written on the two the two terms on the left hand side of the second equation. So of course this is equal to 0, and we see that from here we get an important relation, that r square theta dot is a constant. It is a constant, and typically this is the angular momentum per unit mass, of course, because we have divided by m throughout. The angular momentum of the system. So what have we found from the second equation is the angular momentum conservation of for the planetary motion, right? So r square theta dot is a constant. Let me call this constant as L, which is the angular momentum, which can be found from the initial condition, right? So we'll use this important identity in deriving certain quantities in the planetary motion later on. Okay, so then we call this identity as the conservation principle, the conservation of angular momentum. Okay. So now let us focus our attention on the first equation, that is the force balance along the radial direction, which is this one. So what have we got is, from here we see that m r times r theta dot, what have we got here is, we need to keep referring to the figures all the time. So we are trying to write a relation for the tangential component of velocity, which is v theta, right? So v theta is nothing but m r square theta dot, or m r square omega. So m r square omega is v theta. So that is fundamentally how the tangential component is, v theta is this quantity in the bracket, r theta dot, r omega. So what have we got is that this quantity is equal to m times r, right? And what we further find is that, let me now do a little bit of a manipulation here. R cos alpha v theta by cos alpha, right? And what we see here is that this is m times look at this quantity r cos alpha. So r cos alpha, my alpha is the angle that this planet makes with the perpendicular p. So r cos alpha is the perpendicular distance p, and what we have found is that this is equal to m times p times v theta by cos alpha, right? And now notice that v theta by cos alpha, so if this is equal to alpha, then this is also equal to alpha. So v theta by cos alpha, or v theta secant alpha, is our total velocity v, right? So what have we got here is that this is equal to mpv, right? mpv. Okay, so then what we have is, so this is the relation. So now let us recap this, whatever we have found. M r square theta dot is equal to mpv, right? V is the velocity. Okay, let me keep it magnitude wise. So let me remove the vector sign everywhere. So we are just playing around with magnitude here. So then again, let us go back to the Newton's, the Newton's laws. In the r hat direction, in the radial direction, what we find is that this is r double dot minus r theta dot square is equal to Fr, right? This is Fr is nothing but the total force per unit mass. So this is the force density, right? So then, and along the theta hat direction, we found the conservation of angular momentum. This is r square theta dot, right? So r square theta dot is the angular momentum L. So then from these two relations, we can quickly derive one of the Kepler's law, namely the Kepler's second law. And the law says, I'm just repeating, the law says that the area swept by the planet at equal times are equal, right? So let us look at the Kepler's second law. The Kepler's second law, right? And we have that the area A swiped by the particle P with respect to the initial line. Let me draw the ellipse. So let me call that this is the initial line, and the area A is this following, right? So the area A swiped by the particle P, let me call this as my initial line, right? So the area A swept by the particle P is given by A is equal to integral r square d theta, right? Theta is from 0 to some value theta. So let me call this as the subtending arc angle to be theta. So this is a regular formula for the area of a sector. So area is half r square d theta. Now let us try to differentiate this area with respect to time and see what happens. So what we have is that dA dt is half integral 0 to theta. Let me do a little bit of processing before writing down the final form. So dA dt is dA d theta times d theta dt, right? And what we have is that dA d theta can be found from this integral, and this is equal to r square by 2 d theta dt is theta dot, r square by 2 theta dot, and this is also equal to half L square, because L is r square theta dot, and we know that this is a constant. Okay, so what have we found is that the rate of change of area of the sector with respect to, of course, with respect to time is a constant, or that is the statement of the Kepler's second law, which says that the area swept by the planet at equal times is equal, right? So this is directly, this derivation is directly, the Kepler's second law directly follows from this derivation. Okay. Before leaving this discussion, I just want to mention that this just does not hold only for a central force field, but any inverse square law. So this is a more powerful statement. So what we have said is that the following: the second law of Kepler holds for all inverse square law, right? So the second law of Kepler holds for all inverse square laws. Well, central field is one of them. Okay, so that's a more generalized form of second law. Okay, so now let us shift our attention towards a second conservation law, namely the conservation of energy. I think we are out of time for the first module, so we'll push this discussion in our next module. So thank you very much for listening so far. Thanks a lot.